Hythloday again. Now we're on the induction argument. And I just used as an example explaining how, I used this simple example of two straight conductors to just give an example of the difference between alternating and DC current, and how polarization of voltage is causing how alternating it fixes the blocking problem that creates when you increase pressure at one end and maintain that pressure. Like say I have 150 volts here, it pushes on this, it pushes the electrons this way, but it also pushes them back this way into the battery or whatever. So they can't flow in this direction anymore because they're blocked by the increased pressure here. And that's a very viable explanation of polarization. And that's all I wanted to get to, was the fact that electricity was being induced through the same process of polarization. The polarization creates pressure. So the higher the voltage, the thicker the polarizing filter, the more polarized force that gets to an object, and that's the effect. There's more force where there's higher voltage, less force where there's lower voltage. And that it just ends up being like a push. And when the force goes through, it evacuates everything. The electrons absorb the acceleration. They move, and they move both ways with they move both ways with the direct current. And alternating current allows them both ways in the sense that they clog the cycle. They break the capacity for there to be a circle, and that the circle is restored, the current flow is restored when you alternate the current, because then you keep refilling the bucket so you can empty it, refill it, empty it, refill it, empty it. Alright, so he wants to convert that into a transformer in the more complex sense. This is a simple transformer. You run a current, a coil of wire here and a coil of wire here. You'll induce a charge in this other coil of wire. You don't need any of this metal work to have a simple transformer. It'll still work, because what's happening is when you don't have this piece of metal inside this coil, the field goes straight through, so it flies out. So your field energy is outside the coil when there's no rod in here. But as soon as you put a conductor inside, you put a piece of hot dog in there, nothing's going to happen. But you put a conductor in there, yeah, something's going to happen. It's going to absorb the polarization. The electrons inside the conductor are going to be pushed by the field, and you can kind of see that if the polarization coming in this wire, it can't. If it goes through, it's going to hit the metal. Where if the metal wasn't there, it would go straight through. It would go back out the other side, because it's always going to leave the exterior of a wire. But now with the conductor is conducting the force, conducting the polarization. The electrons in the metal are able to move. They sense the pressure, and they absorb it and accelerate. And they'll accelerate based on the current moving through the wire in a direction. So the current's moving in a direction, it'll push the electrons in the metal in a direction. There'll be a current established essentially in this piece of metal. Now in real transformers, they have a whole bunch of layers of this, because they found out layers work better, because they don't fight with each other as much. It changes how this pressure can move through the conductor. So what's really happening in a conductor is all these are little magnets essentially being created, and all these little magnets have to flip. So say if I have an alternating current, because it won't work with DC, but if I have an alternating current, the magnets are going to flip from this to this to this to this, and it takes time for them to do that. Okay, and so as they're flipping, they get to this piece, and they flip, and they push the current down this coil. And as they come across here, they push the current down this coil. And as they get here, they push it down this way. And then when this 60 cycles, let's say, cycles back the other way, all the magnets switch direction. Then they push the current back up the other way. They push the current back the other way, push it back up the other way. So that's all that's happening, and they're doing it in a different phase because it takes time to push all those magnets. They've got to push all of those little magnets inside of that metal, and that takes a little bit longer than moving an electron. Flipping the magnet, this takes longer than an electron just moving. So that's the difference. It's not a current, it's a magnetic field that's moving through the metal. Well, it's the inductive current. No, it's magnetism. It's converting the electricity into magnetism and then converting it back into electricity. But it's one big gigantic. It's not a gigantic magnet. It's it's just a way of migrating magnetism. So now the field location, instead of it being this radiating out and this coil picking up the radiation is going into the metal and then radiating out of the metal and then radiating out of the metal. So that's the distinction. And he says, I don't account for this. Well, it wasn't my intention to account for it. Again, I'm trying to get the overall theory accepted. I just have to prove the principle, I think. And the principle is proven with the two conductors, I think, adequately. But this is further explanation if you want it. I'm just saying there's nothing I'm not accounting for. You want to say I need to do this to establish the precedent for the principle? I don't think I have to establish the precedent for the principle. And it fits all of the equations for this whole the way this thing happens, and the way the it's the word I'm looking for, the directionality, the whole corkscrew thing and all that, the perpendicular, the fact that the field is perpendicular to the current. I mean, it fits perfectly. So anyway, play some of this.
And more. Now, Emendum speaks of an applied voltage on one hand and an applied voltage at one end of his conductor and a ground on the other, and he's obviously aware of the technical difficulty that when we normally talk of current going from positive to negative, when in actual fact the electron flow is actually coming out of the negative, and so he has a linguistic difficulty to explain in a particular sense.
Well, it's not my linguistic difficulty. Obviously, I think it's a pretty irrational fact of physics that they didn't fix that. I'm just saying, it's the kind of thing where you just say, okay, we got to fix that. That it just screws the pooch.
What's going on? But so, and he said he wants to do this, and I think it's probably a good idea to reverse convention and say. To say, look, forget what you know about electricity. When I'm talking about voltage, I'm talking about electrons, and the electrons are here, and they're pushing that way, and they're trying to get back. They're trying to complete a circuit. Let's say, if I have a battery. Right.
Well, and theoretically, they're not really trying to do anything. They're just responding to the field dynamics. So when there's a bunch of them, they're all polarized. So they're all producing a bunch of, let's say they're red. They're producing all these red quantons, all this red magnetons, electrons, whatever you want to call them. The electrons aren't producing electrons, obviously. They're producing all of this polarization. So the electrons are being pushed away from each other. So they always want to get away from each other. Always. You can put them 10 feet apart and they still want to get away from each other. Yes, it's weak, but it's still there. They're always producing what's hostile to the other. They're never comfortable. So that's the principle you have to understand, is they're never truly comfortable. They're only less uncomfortable. And so they're trying to be less uncomfortable in the sense that anything that mitigates pressure, they'll go there. So if there's any place they can go where there's less pressure, less electrons, if they can find some place to go west, they will go west. But there's no conductor, no place for them to go west, because the pressure is still, like, there's more people in the town next door than the town they're in. They can't go to the town next door. They need a place to go that has less of them.
Now, in this scenario, Mendham makes the point that for a standard resistor, you can think about the voltage declining linearly over the length of the conductor. But I think this perspective is flawed, because...
No, it's not. You have to just think of this wedge as going all the way back to the battery. We know this end of the battery is relative zero. So we know there's zero here, and we know it wedges its way to this 150 volts, let's say. It doesn't have an excess of electrons here, and then somehow there's just the same amount here. No, it wedges all the way the length of the conductor. And we know that the two ends have a difference of 150 amounts of pressure. So 150 quanta of pressure is the difference between one end and the other end, and you're just going with this rational presumption that it's a linear, progressively declining pressure.
In terms of the current and the electrons, the flow, like a fluid flow, the number of electrons flowing here is the same as the number of electrons flowing here.
That's irrelevant. I mean, you're saying it's the same amount of electrons flowing, but the whole point is that's impossible if the voltage is higher. If the voltage is higher, it means there's more electrons there. So you can't say there's the same amount of electrons here as there are here. Obviously, there can be the same amount of flowing, but this is a reservoir. So they're flowing through the reservoir, but this is a reservoir. The reservoir gets smaller and smaller and smaller and smaller, but the flow rate is kind of irrelevant, as I've sort of tried to point out, that the progression of the movement of the electrons doesn't have much to do with this whole thing. It's the polarization that is important, and the movement is only relevant in the sense that it creates which way the push is. But it isn't doing the actual pushing, it's just doing the idea of the pressure exists going this way. You know, it happens. To change from one end having pressure to the other end having pressure, you have to have a point somewhere in there where there's no pressure. And it's that point, okay, that it's that decline, that emptying of the reservoir. So again, it's that idea that the wedge tilts in alternating current. And it's the tilting of the wedge that creates this difference. But you can't really argue that there's fewer electrons at this end, or the same amount of electrons at this end as there are at this end. Clearly, that's what voltage means, is more electrons, more pressure, more, I got to get out of here.
If they are indeed flowing, if indeed and so,
like I said, the directionality doesn't mean anything in terms of how they're moving, as much as what direction they're moving. Direction is much more important than which way. The thing that matters is how much pressure are they going from to what kind of pressure are they going to.
The argument about the nature of the polarization that is given by these electrons here seems to fail on account that there's the same...
I mean, you could say this stuff like, I don't understand this, or you could say, I don't get it. But to say it seems to fail, no, it seems to fail because you don't understand it. I mean, if you don't understand this is a thicker polarizing field, it's creating more blues. Little blue arrows are flying out of this end, a lot more of them that are flying out of this end. This end of this wire has got more pressure to push. It's pushing the electrons to this end. So now the voltage is essentially switched. This one has the high pressure end because this end is pushing more and this end is pushing less. So all the electrons in this end go say, yeah, I'm going to less pressure land. I mean, I'm getting out of here, and then they end up forcing themselves into more pressure just because they all leave town and they all end up in a new town with too much pressure in it again. Ironically.
Electrons are down here. Why would they be polarizing any different?
Well, you can't see the thickness difference. You don't understand. I mean, gee. And you say I'm the one making a flaw. Or I can't do something. You know. I'm just saying the way you're arguing this, to say you don't understand that the size of the magnet decides how magnetic it is, that the thickness of the polarized filter decides how polarizing it is, how much it polarizes, this changes how much of this force is going to exist. How much blue is going to be in this field is decided by the thickness of this voltage. Shit. I mean, it's right in front of you. You can't see the thick, thin. Sorry, but man, that's a little bit too... I'm just saying, it's your style and my style do not combine well. But I mean, I'm just saying, you're saying I'm missing something, I've made a mistake, I'm flawed, and you're missing the fact that this wedge is obviously... you couldn't make a description of thick and thin any more obvious.
And similar, if I open this circuit with a switch, this voltage difference that I might measure with a voltmeter here in the closed circuit situation, I would actually measure that voltage across the switch here. So the voltage would be here, and there would be no voltage drop.
Well, I'm saying there's no volt. If I open the switch, there's not going to be anything. I don't even know what you mean. You open the switch and what? You're putting it through a voltmeter, which is really a current meter. So let's not pretend there's not a distinction. So it's just a pressure meter. So yeah, again, you're just measuring the overall pressure, okay? But you're not measuring the reservoir. The voltage is at this end, and it's obviously not at this end. There's zero here. Okay, if you measure across here, you're going to see the zero here. So let's not pretend that there's a reservoir at that end, because there isn't. There's a reservoir. There's too many here. There's not too many here. So there's a different number of electrons at one end than there is at the other end. The plus end of the battery, the minus end of the battery has more electrons on the surface waiting to get out, and the negative end has... No, the negative end has too many electrons waiting to get out, and the positive end has a bunch of protons saying, I need some extra electrons. That's a fact. And the voltmeter is irrelevant to that fact.
But that would be because there is no flow of electricity.
Well, yeah, so I don't know how you're measuring electricity when there isn't any flow of electricity, so that doesn't make any sense at all. So I don't know exactly what your point there was, except to say you're measuring the battery. Okay, so you're measuring the current in the battery through the resistance of the wire, so presumably it's going to read a little short because of this resistance in the wires. So that's all you've done here, is you've said, okay, let's measure the battery. Yes, the battery will read 150 volts. Obviously, that doesn't mean there's 150 volts here when this switch is closed, right? It means that it's going to progressively decline to zero at this end. It means there's a wedge going all the way through this wire. More voltage, more electrons at one end than there are at the other end.
So that argument about this
Look, put your voltmeter here, okay, and you know, two different places in any resistive conductor, and you're going to read the difference in the voltage. You're going to see the decline in voltage. If I go from here to here, and then read from here to here, and then from here to here, I'll get different readings of voltage.
constraining happening in the other conductor gets confused, or I don't understand that, how this constraining is happening.
This is a polarizing filter. So just think of it as this wire is really thick and this wire is really thin. So just think of this going all the way in 360. So it's essentially a polarized wire. And it's really thick at one end and really thin at the other end. And so it's polarizing all the field energy that goes through it in all directions. And so it's polarizing the field, and so the electrons are seeing a bunch of blue here and very little blue here. So the electrons are getting away from the blue here, and you know, in effect, creating a voltage at that end that's more comfortable than the voltage that the field energy. Being at voltage is more comfortable technically for an electron than having the polarization field pushing them.
Based upon electrons.
They can't help it, okay? They absorb the acceleration. They accelerate. And they can only accelerate through the conductor. They can't accelerate into the atmosphere because it's not a good enough conductor. So they have to go through the conductor. They have to go to the other end of the wire. They have to accelerate.
Flow.
So again, he said the word flaw. There's no flaw here.
Also, the effect of induction, of magnetic induction, is it normally doesn't take place to any appreciable effect when the conductors are inert like this, and it's related.
Yes, it does. It just needs, you need to shove a ton of current through the wire. So you need a thick wire. You have to put a huge amount of amperage through it. But you'll be able to pull these wires together or push these wires apart. So if you put enough current through this wire, you'll do it. There's no problem getting them to fly apart or go together by just changing the path of the current.
To the, what we call the magnetic permeability constant, and that is why we have an iron core.
Well, again, it's called electromagnetism, so there's still an electric component. So you want to confuse the two, that's okay with. I don't really care, but I mean, obviously, electricity, the movement of the electrons, the absorption of the force, is not exactly the same as magnetism, which is the structure of the conductor. So this structure of this conductor, which creates force, is different than the electrons moving through a conductor. So the two things are different. The magnetic disposition of a material is different than its conductivity. They both end up being ways of directing the field energy. So again, as I stated before, as soon as I put something metal inside this coil, I change it from something that's expelling force to something that's consuming force. No force goes out. There's no field around this coil now because you have metal inside of it. All the field is being absorbed by the conductor. And that's converting it, because it's a magnetic conductor, it is becoming magnetized.
Magnetic permeability of the iron core in standard theory allows this flux to
yes, because iron is one of those things. It's both magnetic and electric. It's both a good electrical conductor and a magnetic producer. So it has that unique distinction. But if you made the core out of plastic or some other thing, none of this would work. It's clearly up to this piece of metal to do the conversion of the magnetic flipping into the taking the field energy and turning it into a magnetic transfer of the force.
To form circuits.
I mean, the magnets aren't flipping for no reason. They're flipping because the force is going through the metal, the the electrons, the field energy. It's going through the metal and it's flipping the magnets.
Magnetic circuits, which, if it's changing direction, causes the induction. I'm just going to let the pussycat out.
All right. Well, I'll finish up and see if he has some other relevant complaints for the next video. But yeah, I guess you're just sort of missing the point here. Again, I just want to present enough of this. I think I've proven the principle, and that's all I'm really trying to establish, is that polarization explains the force transfer that takes place with electrical induction and magnetic inductions. I mean, it's simple to understand. It's magnetism. It's just on a surface, so it's a thinner field. But if I put enough electrons in something, it's a pretty substantial field. It's a pretty substantial polarizing substance. Okay. But it's not going to be as effective as a magnet. As a magnet has an atomic structure that makes it more likely to polarize. It gives it a thicker, a more effective polarizing filter. Maybe that's the way to put it. Electricity is not quite as effective. Okay. Not as dense. I mean, it's that simple. Energy is obviously not as dense as matter. It's hard to make a filter out of energy. It's easy to make one out of matter. It's kind of a way to look at it. Yes.